Hello everyone, my name is Alice Delbosc and I'm going to present you my internship work on the generation of nonverbal behavior and conversation virtual agents. This work was done with Magalie Ochs and Stephane Ayache. We focused on the generation of facial expression, gaze direction, and head movements. I will start by talking about the context and existing work. Then there are two main parts in this presentation, the generation of nonverbal behavior and the evaluation of this generated behavior. And finally, I will conclude and provide direction for potential future works. To introduce the subject, this is fundamental to say that nonverbal behavior is very important for virtual agents. They have to move when they speak to follow the rules of human communication and immerse ourselves in the interaction we are going to have with them. Traditionally, the animation of an agent requires the intervention of an animation expert, but with the advances of virtual environments and video games, this is an active area of research and, therefore, automatic models have begun to emerge. The behavior generation task takes as input speech, represented by audio, text, or both, and will generate sequence of corresponding behavior. In this work, as I said earlier, when we speak of behavior, we speak of head movement, facial expression, and gaze direction. Then we use the GENEA platform to animate the generated behavior. You can see one of the characters of the GENEA platform on the screen. So the question is, what system will generate this sequence of movements, which for the moment is represented by a black box? And why is this a complicated task? Because there is many difficulties, such as the diversity and the coordination of generated movements, such as the lack and quality of data we are going to use to train our model, or the behavior, which depends on culture, context, or socio-emotional state of each person, and because there is several possible solutions to fill this black box. We have therefore studied the possible solution through the state of the art. First approach explored for the automatic generation of virtual characters' behavior was based on a set of rules, but due to the number of limits with the rules, the data-driven approach born. To choose the right generation model, we have been inspired by many works, by very recent works, and given the satisfactory results of generative models that follow an adversarial approach, and also good results for those with encoder-decoder architecture, we chose to try two different models. We will enter in the detail of these two architectures a little later. As I said in the summary, there is two main parts in the behavior generation task, the generation and the evaluation. Here, we focus on the generation of nonverbal behavior from acoustic speech features without considering other elements that may influence the behavior, for example, social attitudes, communicative styles, and, in particular, we do not consider the speech content. We concentrate on the objective to generate believable behavior, but not meaningful behavior. We will therefore start talking about the generation. As we adopt a data-driven approach, we need a corpus to train our models. We choose to work on the MOSI corpus, where individuals give their opinion on a film in front of a camera. Then we use two state-of-the-art tools on this existing corpus, OpenFace and OpenSmile, to extract the features we need. With OpenFace, we extract the visual features, those used by the GENEA platform to animate our virtual agents. So we extract the facial action unit, the gaze direction, and head movement. The facial action units are the activation of certain facial muscles. And with OpenSmile, we extract the acoustic speech features like F0, intensity, harmonic difference, and MFCC. So now we are going to talk about our process. We tested two models, a conditional GAN and an adversarial encoder-decoder. Our two architectures use an adversarial approach. Our inputs are the acoustic speech features, and for our two models, we normalize the features before the training. Normalization combined with sigmoid activation layers in the output of our model forced the generating data to be in a range of value determined by our training data. Therefore, the generating data should be close to the reality, and we should not obtain totally unbelievable behaviors. Behavior plays on virtual agents allow us to observe that the speed of the generated behaviors, especially those of the head, eyes, eyebrows, and mouth, are higher than real behaviors. This is why we smooth the generated movements by convolution with a polynomial as interpolation function. This allows us to obtain slower and more believable movements. Now we are going to detail the architecture of the first model. The first model is a conditional GAN, so the generator learns to generate a behavior from the input, that is to say speech features, but also from random noise. The addition of this noise allows the GAN to generate different behavior even if it receives the same segments of speech feature as inputs. Then the principle of GAN is that a discriminator will try to differentiate the real data from the generated one. This allows the generator to be optimized and to adapt itself progressively so that the data it generates look like the real data. This is what the following equation represents. In contrast to Wu's model, from which we have taken inspiration, the layers of the model are not LSTM, but convolution layers. The state-of-the-art have shown that convolutional layers are better in the movement generation task as it prevents the error accumulation, which are specific to RNN. Here are two examples generated with this model.
And basically, these girls try to get one over on the guys all the time by stealing the short.
So, and there's a plot with there's Aaron Eckhart and his crew who are in LA trying to stop the alien.
Now we are going to present the second model. So the second model is the Adversarial Encoder-Decoder. Here, the generator has a more complex architecture. An encoder will learn a smaller representation of the acoustic features, and decoder will decode this representation into head movement, gaze duration, and facial action units. So we supervise our generator with the mean square error of the gaze orientation, head movements, and facial action units. You can see the equation on the screen. But we are still in an adversarial approach, so we still have a discriminator, which by trying to differentiate the real example from the generated one, will help the generator to optimize itself. And we therefore have the following adversarial loss function. Finally, combining the adversarial loss with the direct supervisory loss gives the following function. With W set to 0.1, we ensure that each term is equally weighted. By setting W to 0, we obtain a model without adversarial loss, which we consider as our third model in order to evaluate the effect of adding a discriminator. The architecture is inspired by UNet, a model that does image segmentation. You can see the architecture on the screen. What's very important in our two model is that the generator will not only try to know if the generated behaviors are believable, but also if they are believable with respect to a given speech. So the inputs of the discriminator are the speech features and the generated behavior or the real behavior. Here are two examples generated with this model. We use the same segment of speech features than the two examples you see with the first model.
And basically, these girls try to get one over on the guys all the time by stealing the short steal.
So, and there's a plot with there's Aaron Eckhart and his crew who are in LA trying to stop the alien.
We finished to talk about the generation part. We are now going to talk about evaluation of the generated behavior. The quality of a behavior generation model can be assessed using objective measures, and/or subjective measures. Because we do not have the same task generation as previous research works, we cannot evaluate our model by comparing our performances to existing models. But for objective measures, we use the loss function, largely used in deep learning, the density estimation of the generating data, and then likelihood that the real data belong to this distribution, and visualization of PCA of several generated images versus real images of video. We confirm that the loss function is not adequate at all for our task. Behavior can be very believable while not corresponding to the behavior of the initial test set of the initial video. If the initial video raises the right eyebrow, the same effect can be produced by raising the left eyebrow, yet the loss function will give a high value. This method also tends to ignore small deviation in behavior, which for a human distorts its entire perception. So based on the two last objective metrics described, we select for each of our models a good architecture and a good combination of hyperparameters. It gives us an indication of the believability of the generated behavior. However, they remain insufficient. For example, they do not measure the coherence of the behavior with the speech, or they don't measure and evaluate the adequacy of the behavior speech. So, subjective evaluations are crucial since the objective measure cannot assess all the complexity of the social communication. But objective measures remain necessary because subjective evaluations are very expensive and time-consuming. So for subjective evaluation, we ask participants to evaluate the generated behavior on two criteria, naturalness and coordination. So you can see here the two direct questions we asked to the 31 participants. We asked them to rate 15 seconds videos, either generated or simulated with ground truth. On each of the criteria, they use a 5-point Likert scale ranging from 1 strongly disagree to 5 strongly agree. And you can see here the table with results, with here the first model, so the conditional GAN, here the second model, so the Adversarial Encoder-Decoder, and here the second model, but without discriminator to evaluate the effect of discriminator. The average of the score tends to show that the best model is the second model in terms of coordination and the third model in terms of naturalness. So we can conclude of the superiority of the auto-encoding architecture, which by representing the speech feature in a smaller representation and then decoding each of the visual features independently, allow us to obtain results significantly superior than the first model. Unfortunately, none of the two criteria obtain a significant difference between the second model and the third model. The results are different from what we expected. Indeed, we expect that the addition of the discriminator improves coordination, but the lack of significance does not allow us to draw such conclusion. These results may be explained by different reasons, so maybe the discriminator, by avoiding convergence towards the average, increase believable and expressive behavior, but as a result, behavior are perceived less coordinate. Or maybe user tests are performed on very too short video, and longer video could lead to different results, like revealing repeated behavior for the third model. Consequently, in the next evaluation, we aim at evaluating video with longer duration and on a larger set of participants. Compared to the state of the art, the contribution of the work presented in this paper are a model that jointly generates the head movement, the gaze direction, and the facial action units. An action unit-based behavior generation model improved the interpretability of the output of our model, and therefore we are able to manipulate the generated facial expression more easily than 3D coordinates. Contrary to existing research works, we propose to consider numerous speakers to cover a wide range of speech styles in our datasets. There are a lot of important perspectives for this first work. For example, improve lip animation. We choose here to blur the mouth area. In our preliminary experiments, we noticed that the participants' evaluation were strongly linked to the accuracy of the lip movement. So in the first subjective evaluation, we blur it. Create an hybrid approach for mixing the rules and the data-driven approaches, or take into account a didactic interaction environment. This was the modeling perspectives. We can also improve the evaluation by integrating new metrics able to compute the speed and coherence of behavior with speech, or simply conduct larger subjective studies. Thank you for listening.